All right, so this section we are looking at alternating series test. So what is the alternating series test? And then looking at what remainder means. And then we'll look at the definitions of absolute and conditional convergence. So let's get started. So to start off with, what is an alternating series? An alternating series is any series that you can write. It's possible to write it in this form where you have a -1 to an n power or an n plus 1 power. And that's times some other series b sub n. So we're taking b sub n and then we're alternating what it's going to be, positive or negative or positive, depending on if we have the n plus 1 or the n, and where we're starting for our index of summation. If our first term is going to be positive or negative, but every term is going to alternate signs, positive and negative, on and on and on. And so you're going to prove in your groups some things with this alternating business. Like if we have an alternating harmonic series, does that converge? Yes or no, and why? So we have the alternating series test where we have a sub n. All of these we're going to say that they are positive. So we have alternating series where it doesn't matter like if we have starting on n plus 1 or n, if that's going to be positive or negative, but we are going to have this alternating series. We have convergence. We know that this converges if we have these two things. If we have our a sub n, that the limit as n approaches infinity of that gives you 0. So we have like effectively our nth term test, but just for the a sub n, not with this alternating business. And if a sub n plus 1 is less than or equal to a sub n for all n, meaning that a sub n is monotonic and decreasing. So a sub n is a series that is a sequence that is non-increasing. So it's either staying the same or going down for all values of n. So think a little bit about how this might be proven, and then we'll talk about it. So if we know that we have an alternating series, and let's just, for generality's sake, let's just look at this one. If we're looking at this alternating series, we know that that whenever our n is, like whenever we're looking at an even number, then we're looking at like pairwise things that we can kind of group together so that our partial sum, our even partial sum, so s sub 2n, so this is an even partial sum. This is going to give us like a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus a sub 5 minus a sub 6, and so on, right? And that's going to keep on going until we have plus a sub 2n minus 1 minus a sub 2n. So the previous term minus this last 2n term. So now if we take this sum and then we group it together, so we take like these, we add all of these up, and because of the commutative property of addition, we can do that, right? And then we group all of the subtractions together. So if we do that, then we end up with that we have a sub n minus 1, like all our odd terms, that difference happening, and then when we have this, then we know that this is going to be bounded, right? Because we have some numbers that we're also taking, like we're taking these numbers, but then since we know that we have boundedness here, well, our n behavior, all our a sub n's are going to 0, then we know that we have convergence. And since we have convergence for this partial sum, so that we know that limit as n approaches infinity of our partial sum of even terms is going to give us a number, and then we're adding in a limit of this last thing, right? N approaches infinity of a sub n. That is going to give us our a sub n, 2n minus 1 partial sums. We have, let's move this. So we have that is going to be equal to the limit as n approaches infinity of s sub 2n minus 1. So we have this for any of our n's that we're looking at, that we get a number plus something where we're getting this going to 0, right? Because this is going to be 0 from here. So we're getting a number L plus what? Nothing. And so we're getting out a number L. And therefore we have convergence, because of the monotonic decreasing and because we have this part goes to 0. But really, for alternating series, I think the helpful thing is to remember middle school dances and how awkward they were. So, middle school dances is where, you don't really know how to dance. And I mean, like, you might now know, but most middle school students did not know how to dance, which is totally fine. But middle school dancing, you just go from side to side. You just take a step and take a step and take a step. But the awkwardness of middle school is that each step gets smaller and smaller and smaller and smaller until you eventually just stop moving out of awkwardness. And so the steps getting smaller and smaller, that's the monotonic decreasing. And they're alternating sides, right? So it's positive, negative. If you're thinking like the center point is 0 and then moving to the right, moving to the left, those are alternating signs. And as your steps get smaller and smaller, as the limit of them goes to 0, then you have convergence, you're going to stop moving. So, hopefully that helps, and sorry if that brought back memories of awkward middle school dances, but it's okay. So, for determining the convergence or divergence of this series, what should we do? Well, this says tip number 1 for series is to write out terms. And so that's pretty much, that's what we should do, just like when we're trying to tackle a series, just write out some terms. So what happens to this? We get, if you plug in 1, then you get positive 1 over 1. And then plug in n equals 2, you get negative 1 over 2. And then plug in n equals 3, and you get positive 1 over 3, and then negative 1 over 4, and so on. So this is an alternating harmonic series. Right, so since it's alternating, we can use the alternating series test, because you already thought through, okay, is this going to be does this follow with the nth term test if we're looking at our n's going to infinity? Is this going to 0? Yes. So it could converge, and then you think, okay, well, is this like any of our other things? Like, is it a telescoping series or a piece series, or is it a geometric series? And you're like, not really. And then you're thinking to yourself, well, what if we could do, like, can we use the interval test? Is that a good way? Or maybe direct comparison or limit comparison? And like, this alternating business, that's making it kind of hard, but hey, we just learned the alternating series test, so let's use that. Alternating series test looks at, is the limit as n approaches infinity of a sub n equal to 0? Yes. And is a sub n plus 1 less than or equal to a sub n for all n? Yes. So by the alternating series test, this converges. Boom. But writing out the terms, that's the first step that you really should do. So, tip number 2 for series is to write out terms. Oh, I see. Okay, so we should write out terms. So we're determining the convergence or divergence of this. And, let's just write some terms out. So what do we get? This is equal to 1 over negative 2 to the 0, which is what? Negative 2 to the 0 is just 1, so that's 1. 1. plus 2 over negative 2 to the 1, which is what? Negative 1. Plus 3 over negative 2 to the 3 minus 1 is 2, so that's plus 3 over 4. Plus 4 over negative 2 to the 4 minus 1 is 3. So plus 4 over negative 8. Plus 5 over negative 2 to the, what is 5 minus 1 is 4. What's that, 16? So plus 5 over 16. Alright, so we wrote out some terms. Great. And then plus so on. Is that going to converge? Well, let's think. It's an alternating series. Do we have n, a sub n plus 1 is less than or equal to a sub n for all n's? Oh, also, does a sub n go to 0? Is that going to give us 0? Yes, because L'Hopital's rule, right? That we're thinking, like infinity over negative 2 to the infinity minus 1, but that's going to give us 0. Yeah. Okay. And then, is this true? Well, we have 1 and then 1, but that's okay because we have less than or equal to, and then we're going down. We got 3/4 and then a half, and then 5/16 and so on. Our denominator is growing faster than our numerator. So, by the alternating series test, converges. Oh. So for this example, we have terms written out. Nice. Thanks, example. We do have an alternating series because we have negative 1 to the n plus 1 power. There are other ways that we can have this alternating business. Like think about what kinds of functions go up and down, and then if we can pull specific points from that, then we'll have alternating things like maybe sine and cosine. And then, okay, so we have an alternating series. Do we have the limit as n approaches infinity of a sub n equal to 0? Well, that's looking at, is the limit as n approaches infinity of n plus 1 over n, is that equal to 0? No, it's not. That's equal to 1, because we have n plus 1 over n, so that plus 1 in the numerator is going to be negligible. You're going to end up with just like pretty much the same thing over the same thing, or you could do L'Hopital's rule if you really feel like it. And so this diverges, or this does not converge. So we can't say that it diverges right off the bat, but we can say, well, this is going to, wait, we can't, because of the nth term test, we can say that this does not converge. It diverges. Alright. Diverges. I guess divergence is not diverges. This diverges. Alright, so for this series, we don't even have like a sum to look at, so like that's kind of sad. But is this alternating? Yes. Right? Positive, negative, and so on. Does the limit as n approaches infinity of a sub n go to 0? Well, like our term value is going to 0. Well, we're getting like 2, 1, 1, 1/2, 2/3, 1/3, 2/4, 1/4, and so on. So it looks like they are going to 0, but is a sub n plus 1 less than or equal to a sub n for all n? I guess in our natural numbers. No, because we have this right here. We have 1, our 2/3 is our next term, and that is greater than 1/2 right there. So our next term is greater than our previous term, so we kind of apply the alternating series test, and so we can't say if it converges or not based on the alternating series test. And so, well, but actually, like, our partial sums are going to be a divergent harmonic series, right? Because, like, we're taking our top number and we're just alternating between 1 and 2, right? The top number is just 1 or 2. But our denominator is n. So this is going to give us, if we regroup this, we're going to have our harmonic series minus another harmonic series. And those harmonic series diverge, so this diverges. And the reason we could pull that pattern out is because we looked at the terms that were written out. So we have a remainder with our alternating series, and that remainder can be determined where, similar to kind of when we're like doing division, right? When we're doing like polynomial long division or just regular old long division, you're going to have a remainder. That's kind of the idea with our alternating series. Like at a certain point, we can say like, and after this point, the difference between what our calculated value is and what the actual value is for our infinite series is less than this number. So if we have a convergent alternating series that satisfies this condition, which is part of our alternating series convergence, then the absolute value of the remainder, R sub capital N, involved in approximating the sum S by S sub n, which is our partial sum, our capital Nth partial sum, is less than or equal to the first neglected term. So it's the first term that you don't use. So if we're looking at like a sum for like negative 1 to the n times 1 over n, right? It's our harmonic series. Then, and we're looking at, I don't know, like the fourth partial sum. So S sub 4 is going to give us, starting at 1 to infinity. So if we start at there, then we get negative 1 over 1 plus 1 over 2 minus 1 over 3 plus 1 over 4. So this is our fourth partial sum. The difference between our actual sum, which we're going to call this S, so the difference between S and S sub 4 is going to be equal to the remainder of 4, which is less than or equal to our next term, which is going to be 1 over 5, right? So it's our difference is 1 over 5 for like between our S sub 4 and our S sub 5, our fifth partial sum versus our fourth partial sum. The only change is that we're subtracting out this 1/5. And so if you think about, like, go back to the analogy of the awkward middle school dancing, if the step is smaller, then every step after that is smaller and smaller, then the difference is going to be bound above by this next value. And hang on to this idea of remainder, because we are going to come back to it. It's going to be so great. But alternating series remainder, our difference between our actual thing, our actual infinite series, and our nth partial sum is bounded by our next term in our series. So if you're asked to approximate the sum of this series by its first 6 terms, then we're looking at this S, that's capital S, right? And then we're looking at our first 6 terms, so our sixth partial sum. And so our S minus S sub 6, that's going to be, the difference for this is going to be R sub 6 remainder on our 6th. And so what's going to happen for our 7th term, our 6 plus 1th term, which is 1 over 7 factorial. So this is going to be less than or equal to 1 over 7 factorial. But that doesn't really help us find the approximation of our sum. So the approximation of our sum, we need to find what this actually is, this s sub 6, and just through some arithmetic, I'm going to get this is like 91 over 144, and I did not just do that in my head, I have this written down. So our actual sum is going to be 91 over 144, and then plus or minus, it's going to be, oh, sorry, that's bad notation. So, S is going to be between, I should write this somewhere else. Okay, so we have S. S is going to be between 91 over 144 minus 1 over 7 factorial and 91 over 144 plus 1 over 7 factorial. And so we know that within this band is where our infinite series, what that number is going to be. And if you want to plug those into your calculator, that's great. But, I mean, that's like pretty dang good. We just use like 6 different, we add together 6 terms, and then we know within a 1 over 7 factorial, how our series is going to behave. Like what the number that's converging to is going to be. It's pretty amazing. Because like 1 over 7 factorial is like very small. So, absolute convergence implies convergence. If you know that the absolute value of your series converges, so the non-alternating thing converges, then your alternating one converges. And so think about how you're going to prove that with your group, because I think you will have a really fun time with that. Because like think about the, and then think about some counterexamples or some things that don't satisfy this. If we have our alternating series is our harmonic series, then the absolute value of it doesn't converge, even though the non-absolute value, the alternating version of that series converges for the harmonic series. Harmonic series is one of the classic things. You just like try to see if it, how it fits into whatever theorem we're looking at. It's quite lovely. And then some definitions. So we have absolute and conditional convergence. They're different because we just needed more than only convergence and divergence. We now have absolute convergence and conditional convergence. So we have a series is absolutely convergent if its absolute value also converges. So our harmonic series is not absolutely convergent because its absolute value doesn't converge. So it would be conditionally convergent. A sub n is conditionally convergent if the sum of a sub n converges, but the absolute value of a sub n diverges. So for this, again, our harmonic series, alternating or not, that changes the convergence or divergence of it. So our alternating harmonic series is conditionally convergent. So what's going to happen to these? Pause the video, think about it. So I'm thinking that for the first one, n factorial versus 2 to the n, which one is growing faster? And actually n factorial starts off a little bit smaller, but will quickly overtake what's happening. Because then you end up with what, like 4 factorial over 2 to the 4th, so you're multiplying 4 times 3 times 2 times 1 over 2 times 2 times 2 times 2, so the 4 is going to make that stronger. And so on. So by the nth term test, this diverges. Diverges. What are the next one? Well, it's alternating. We got n to the 1/2 power. So what is that? It's p series, right? And so we have an alternating p series. P series converges only when p is greater than 1. So a harmonic series and anything smaller for our power is going to not have convergence, but by the alternating series test, we do have that the alternating series converges because our terms are all going to, the limit of our terms goes to 0, a sub n goes to 0, as n approaches infinity. It's really bad notation, sorry. And a sub n plus 1 is less than or equal to a sub n for all n's. So this converges, so B is conditionally convergent. Conditionally convergent because the absolute value does not converge, because that's a P series where P is going to be less than 1. So the absolute value is not going to be absolutely convergent, but it is conditionally convergent. All right, last couple, and then I'll show you some practice problems that you can work on your own. So we have determining the convergence or divergence of these things. What is happening here? For this first one, we have -1 that's raised to some crazy power. And what's happening in this power? Well, are we having alternating each term? Like, do we have an alternating series? Can this be rewritten as -1 to the n power or -1 to the n plus 1 power? Do we have alternating each term for our sign? And the answer is no, because we're doubling up. And so that means that this is not an alternating series. And so we're kind of sad about that. So this is not alternating, but what is happening to it? Well, effectively we have 1/3 that's being raised to the n power with some sign changes that's happening. And this is a geometric series, right? Where r is going to be 1/3. 1/3 is less than 1. And so we have a convergent geometric series for the absolute value of this guy, right? The absolute value of this gives us a convergent geometric series. And if we have absolute value of our series that converges, then we have a absolutely convergent series. So this converges absolutely. Okay. What about B? Well, that clearly is a alternating series where there's no funny business going on in the numerator. We just have -1 to the n. And then we're doing that over natural log of n plus 1. So that is going to give us, what's going to happen there? We have limit as n approaches infinity of 1 over natural log of n plus 1. Where's that going? That's going to 0. Right, because our denominator is going to infinity, so 1 over infinity is 0. And natural log is a monotonic increasing function, so its reciprocals are going to be monotonic decreasing. And so we have that our second condition, our a sub n plus 1, is less than or equal to a sub n for all our n's in our natural numbers. And so B is going to be, it converges by the alternating series test. What kind of convergence is it, though? Is it going to be conditionally convergent or absolutely convergent? Well, we could, maybe we need more space. We could use the direct comparison test, right? Because compare this with like 1 over n. So with 1 over n, that's going to be less than 1 over natural log of n plus 1. Right? And then if we're looking at this series, well, this diverges. So then by the direct comparison test, that also diverges. So the series that we're given, this one, this converges only conditionally. And direct comparison. So conditional convergence for this alternating series. Alright, so be ready to do a quiz on at least one of these problems kind of soonish. I'll move that over. So strongly recommend that you try some of these, and you see like negative ones a lot of places, but over here and there, you know, we have this sneaky way of saying that we actually do have an alternating series. So look at those, think about them. I mean, 29 looks really fun, very brain bending, and 20 looks like a good one too. Like, these are some good problems, so try some of these out. Have fun. See you later.